Hi class, this is Miss McConnell.
And Mr. Huff?
We are going to summarize what we did in class today, including some of the conventions and terminology that we talked about. To begin, we want to talk a little bit about how we derived the x and y coordinates for this pi over 4 right triangle, which would be pi over 4, and pi over 2, which you might be more familiar with, and it is totally okay to reference that this is a 45, 45, 90 triangle. I've seen two effective methods to be able to do this, but before we talk about the effective methods, I really want to remind you that Mr. Huff and I anticipate that a lot of you are going to simply try to memorize, and we really want to discourage you from doing that. So you can anticipate that we will ask you questions that require you to understand how this is derived. We might ask you we might tweak it in a way that doesn't apply to just the unit circle, and you're going to have to be able to understand how to derive that knowledge using specifically right triangles. And so I saw two methods to kind of think of this triangle. One of them was to think of the method with these two triangles holistically, thinking of this as a 90-degree angle, and then the large triangle is 45, 45, 90. And then you can set up your Pythagorean theorem as 1 squared plus 1 squared equals c squared, and then simply solve and get that c has to be a length of square root of 2, which would get you this entire length. And therefore, in order to get the y coordinate, which will be this vertical length, we can simply divide that in half, since these make up this triangle makes up half of the whole triangle. And so from that, you can either set up the Pythagorean theorem again to find what this third missing side is, or students identified, since this smaller triangle is 45, 45, 90, that this length will be exactly the same as this one because it's isosceles, which gets you an x coordinate of the square root of 2 over square root of 2.
And alternatively, there was another approach that was taken in class, and I'll do it on this side over here, where students were looking at just a single triangle, single reference angle in one of the quadrants at a time, and same recognition that this was 45 degrees and that this is 45 degrees and that this was 90 degrees down here. And they recognize, well, this is some unknown length and this is going to be the same unknown length, and so they labeled them x and x, or a and a, or b and b. It doesn't really matter. And from here you can then use the Pythagorean theorem because we only have one unknown to solve for. So it would be x squared plus x squared is equal to 1 squared. So 2x squared is equal to 1. Divide by 2. X squared is equal to 1/2. If we were to root both of these, x is equal to 1 over root 2. And then rationalizing this would be root 2 over root 2, which then gives us x is equal to root 2 over 2. And so now we know that our x value here is going to be root 2 over 2, and this x value and this x value in this case, which is this x value, which is actually the y coordinate, is just labeled with the same variable, would be root 2 over 2. And so this distance from the origin along the x-axis is root 2 over 2, but negative. And this distance from the x-axis up, the height or the altitude of this triangle, is then root 2 over 2. And since it's in the positive direction, it remains positive.
And so then you were able to think about this would be the same distance but negative, and so that is going to give us a negative square root 2 over 2 as our y coordinate. And then you have this negative x coordinate of negative root 2 over 2 as well. So then we have this would be negative for the y value, and then we see that the x coordinate would be positive. And again, we're really looking at lengths here to determine, and then of course your direction.
Yeah.
Now, what we've just shown you here is a reference angle diagram. That's what this type of diagram is called, just a reference angle diagram. And the reason is because all of these values, these pi over 4 values that you see here, are called reference angles. And reference angles are simply, I'll draw an arrow here, they are simply the value, and I'm going to have to introduce some other terminology here, so let's start there. We have this would be when we measure an angle of rotation in standard position. This is where we start our rotation. And we call this the initial ray. This is the initial ray, or if you're referring to the triangle, you could call it the initial side of our angle. Whereas this one would be our terminal. It's the ending side of our angle. So this is the terminal ray or terminal side.
And another key distinction is your reference angle and your terminal angle, or excuse me, your angle of rotation can be the same, but they are not necessarily the same. It just so happens in this first quadrant here, when we're looking at pi over 4, the angle of rotation from the initial ray to the terminal ray is 45 degrees, and it happens to be that the reference angle, the angle created from the initial side and the terminal, or from the x-axis and the terminal ray, is also 45 degrees.
Exactly. And so to clarify, pi over 4 is still our reference angle here because it is our terminal side as determined by the standard position, but it is from the terminal side to the x-axis. And so that's the measure of the angle there. Whereas our angle of rotation would be that 3 pi over 4, because you could think about this as, if this is pi, it's pi over 4 less than that, or you could think about it as pi over 4 plus pi over 4 plus pi over 4. So this is our angle of rotation, which sometimes is the exact same thing as the reference angle, whereas the reference angle is just that measure to the x-axis.
It's the angle in reference to the x-axis,
Yes.
which is where it gets its name.
Exactly. Now, this is the first part of the video, and these are just some terminology with the reference angle diagram. In part 2, we're going to talk about how could you make a reference angle diagram for that other special triangle that we've seen, and how we see this reference angle diagram in our circle. How do we apply that to the circle with all of our special angles measured?